just want to give an intro to Håkan Råberg. I spent half my time at Juxt on projects and consulting, and then the other half is trying to get Håkan to work on my projects. Because he was the chap that introduced me to Clojure. And what I find about Håkan is that he's always trying to strive for simplicity. And just when you think you've got up with him, he just takes it to the next level or down to the next level. So, yeah, this is his talk. So, without further ado.
Okay, thank you, John. Yes, I've been working with John on and off for more than 10 years now, since I moved to London. So I'm very happy to be here to speak at the Juxt conference. So I'm going to try to continue, well, some of the, not necessarily fourth, but a kind of low-level theme. So my talk is called The Search for Simplicity, which I'm going to give you a spoiler. I didn't actually find it. So background. I worked on the RDF semantic web project, and I was quite excited about this. I always felt like semantic web has promise. I don't really believe in it fully, like something is a little bit too idealistic maybe, but I was like, I got a chance to work on this, like to try it out. This project was interesting, but I wouldn't call it success. So I need to regain sanity after actually working on this. I need to kind of reboot my brain. Everything was so abstract. We kind of took it like meta model. Everything was quite extreme on this project. Every time you tried to actually do something concrete, you felt you were doing something wrong. Or someone came to tell you, like, that's good, but we actually need to kind of go through these hops again. So it felt a little bit like kind of old school, kind of UML-based development. You had some architect telling you didn't do the right thing. Okay, so I tried to regain sanity by actually going low, by writing a scheme compiler in assembler. So I was like, I haven't coded assembler for a while, so it's maybe time to kind of revisit this. And, well, I'm not sure if this was a good idea or not, but I definitely learned some things on the way. So I'm going to try to kind of I only have 25 minutes, so it is sadly not going to be as deep and multifaceted, but I'm going to try to give you a taste of what this was like. So back in the early 90s, back in high school, before high school, I had an Amiga, like many people in my generation, started tinkering around with 68K assembler. I tried to achieve things. I never ever got to anything close to what Carsten was showing. Because there was a big gap in actual, in one way back then, you had one machine which you could potentially understand, and you learned a lot about it, and you had a lot of time to tinker with it. But when you run into a problem, you didn't necessarily have an easy way to get more information. You had a few books, you could recall some BBS, you could try to pester some people at school who potentially knew more than you. But in general, at least where I was, you quickly reach a local maximum, which was quite low. Okay, I know this stuff, I can kind of play around with it, but actually, I don't know where to go with it. A bit later, I also coded a bit in high school. We managed to pester our teachers to actually start an assembly course in high school. So we did that. So that was quite interesting as well. If you have ever coded either Motorola assembler or later Intel assembler, you will moving to Intel assembler doesn't feel like a nice step when you're coding by hand. It's quite. Back then, you had to use segments. If you're going to divide a number, you have to put in a specific register. It doesn't feel as clean as Motorola assembler, basically. So basically, after this, I was working for a programmer, not in assembly most of the time. Started professionally in Java around 96, 97. Did other languages, now mainly do Clojure, but never assembly, right? So I decided, okay, hopefully I've learned something during these 20 years. I learned programming back then. So all my programming career has been shaped by this experience, you could say. But I never actually tried to revisit this for many good reasons, and still quite good reasons not to revisit this. But I decided to, okay, I have some time. I need to go low level. I feel like going low level. So basically, what has changed since, if I'm going to fuse these two things, I have a professional programming experience now for 20 years. I have a childlike or teenager-like joy and frustration of learning to program. And that is still forming this. If I go back, can I actually pick up something new? This was kind of my thinking. And again, the simplicity part is I was working on basically in Lisp, in high-level languages, in JVM. I was I want to gain something. I want to what does it feel to go back to where I started? Of course, that's tickling impossible. You can do retro programming. I do not want to do retro programming. I don't want to go okay, I'm going to code a Commodore 64 demo or something. It's cool, but that's not what I was interested in. It's okay. So I'm not sure if anyone of you are back then, this is SM1, which is a kind of simple assembly IDE for the Amiga. So this was probably the first not exactly this version, because back then different programmers tended to get the source for this, maybe patch it a little bit. Like you third generation got someone's kind of patched version of something, and then you start trying to use it. And there were no manuals or anything usually, so you kind of, okay, let's see what happens. But this is how it looked. Like, it's very lightweight. And the point I want to make here, also about simplicity, is that while these computers were quite constrained, the feedback loop was usually quite quick. So as long as you kept it low level, right? Like, so an assembler on Amiga was simple to work with. You could easily do it. Programming C on Amiga was also possible, but before you had hard drives and things, this was not necessarily very convenient. Like, I remember programming some C, trying to write a C program. I had like 5 disks you had to kind of swap around. Back then, you kind of, like the actual diskettes, you had to swap in and out to compile. So, but while the feedback loop was good, one problem with this entire approach, like, there's no memory protection. It's like a single computer. So as soon as you made any mistake, you got this, right? So I'm not sure if anyone remembers, but it's like your Amiga crashes. Okay, if you're lucky, you can potentially figure out what's going on. Otherwise, you basically have to reboot, put in your workbench diskette, your basic operating system diskette, start it up again, and then go back, hopefully, to where you were leaving off. So this was my dream, to own this, like actually buy an assembler. I tried to convince my mother to give me this, but she didn't see the purpose or see the future in this investment. So I never got this, actually. But this is like DEPAC 3, and it's the new standard, as we can see. It actually doesn't mention what it is, interesting enough. Like, but it says on the chip here, you can actually see this is from 91. So this was like released 1991. Here's the back, so you get like a debugger, you get an assembly, you get lots of cool stuff when you get this package. But I want to just show you this, because this is like totally random. These guys, Highsoft, they're in Bedford, Milton Keynes somewhere. And they still exist, actually. But they're doing web development these days, I think. But it's like, again, diskettes. I know most people have probably seen them, but like if you haven't seen diskettes, like it's fun, like you're getting older. Like some people have never worked with diskettes, right? This is actually 2 versions of the same assembler for 2 different versions of the Amiga operating system. So you only use 2 diskettes once you got it, if you ever got it. But this is actually, these diskettes, the 880K, so basically this entire fancy IDE was less than 2 megabytes, which obviously much less than this slideshow. Yeah, later we used this, which is, yeah, the turbo assembler. This is like, if you ever use like Turbo Pascal or any of these kind of like, you remember like the blue, like yellow and blue kind of DOS-based IDEs on the PC, this was one of those in that series. So this was what we managed to convince our high school to buy for us, and then sit around and tinker with for a semester. Here's interesting. This is total. I could claim that this was actually something I thought about when to embark on this project, but it's not. But you can see here's Tiobi. So at number 8, this is today. Assembly language is back. It's climbing. So it's like, so if there's an assembly jobs out there. Actually, by the way, if someone here knows assembly for real, don't laugh too much once I start showing my assembly I've written. But I think this is probably for mobile, for IoT, for embedded, and stuff like that. Other people may have better theories why it's climbing back up, but it's there. I'm not sure if it's, I don't think it's related, but you see the big drop in C there as well, which is a black line. I don't know what that is, but maybe it's like Rust, Go, other things. Okay, so when you think of garbage, think of Akeem. This is a quote from Coming to America, which is potentially the best Eddie Murphy movie. So, yeah. So my scheme is called Akeem scheme, which is called assembler scheme, and it's garbage. Self-proclaimed garbage. It implements maybe 60 to 70% of scheme 7 small. So most people have potentially coded scheme at some point in your life, but you probably have coded, unless you do it professionally with Racket or something, coded scheme 5, which is the one you learn in structured interpretation of computer programs. So scheme 7 is very similar. It has a little bit fewer features, a little bit modernized. It came out, I don't remember exactly one, but, well, the last 5 years at least. There's also something called scheme 7 large. It doesn't exist yet because they are kind of this kind of common Lisp hell of trying to kind of define a larger subset of standards which are actually going to be able to write the real programming in. Like, you cannot really write anything useful in scheme 7 small. Like, so you can write a file to disk, you can write a character to screen and stuff like that, but you cannot, there's no network and there's no general things you can actually use. But still, when I started the project, I was like, this project needs to be hard enough for me to not know I would be able to make it. So I'm not sure if you guys have seen, like, there's something called Make a Lisp, which is this funky thing, which is like there are like 100 dialects of a single simple Lisp. I decided like I'm not going to do that because I knew somewhere like yes, it'd be painful, it'd be hard, but I'd probably pull it off. Let's aim a little bit higher. Then I became motivated to actually try, right? So I decided very early on that this is going to be a template-based just-in-time compiler. I'm going to show you exactly what that means in a few slides. But I also, after deciding and being quite happy, like, oh, this is a cool technique, I read some papers somewhere like that no template-based compiler can actually be called a real JIT. It's like they're basically garbage. So, but I stuck with that because doing something else would have been way too hard for me at this point. I ended up with around 5,600 lines of handwritten assembly. Like this is modern, like x86 64-bit assembly. I wanted to kind of like, how does assembly feel to work with today? How is it actually like? So this is what I ended up with. On top of that, I layer around 1,600 lines of scheme. So basically, you bootstrap your assembler. Eventually, you can start writing more and more things in scheme, and then like you have your entire scheme thing. Right? It uses glibc because this is a bit like a cop-out, but I realized like I don't want to use syscall. So like I didn't want to make this an exercise about converting like doubles into characters and stuff like that. It's like, sure, you can do that, but it's just going to be a lot of work. So I used glibc because I felt that that's kind of good balance. Like basically, it's like this has to work on a normal Linux or Mac like machine. This is maybe like on a methodology point of view. When you want to write an assembly program, you quickly realize there's no like ASM unit. And that's kind of for good reasons. You realize that you actually, if you want to test your assembly, the most normal way to do it is to write your unit test in C and call into your assembly. I felt that was a bit too much ceremony, so I decided I'm going to do this approach instead. So obviously everyone knows what diff is, but enter is a file watcher, like a Linux or like potentially on Mac as well, but it's basically a Unix-style file watcher. So anytime a file changes in the files that you give it, it will return, right? Like so you can chain the command. It's more Unix composable. Anyway, so I had this loop using enter, watching all my working files, and every time they changed, I ran my unit tests, which are basically just a scheme file, printing out loads of stuff, diffing it to my golden master. That approach actually worked very well. It was very, very, like every time you saved, you got feedback. I found some kind of funky diff one-liner from Stack Overflow, which made it very nice and like readable. So good approach, I would use again. I decided my first goal was to have tail call optimization, because if you want to write the scheme, you kind of want tail call optimization. So that was my kind of first stopping point. So let's get to there. But then I continued I did call with current continuation. I'm not going to go into what it is if you don't know, but it was quite hard. I did varargs, and then finally I added some foreign function interface, so you can call into C functions as well from my scheme. I did a basic GC. Again, this was not an exercise in garbage collection technology. Like I read a lot of garbage collection papers, but I realized one thing you quickly realize when you're writing an assembler, you want the techniques you're going to implement to be quite simple, because you have you don't have much abstraction to work with. You can very easily code yourself into a hole if you're trying to write something complicated. So basically, I implemented like a very basic stack data structure, which I used for everything, and that's kind of it. You don't have a hash map, so you start using arrays a lot. Like, can I figure out how to index something by an integer? That's good. Like hash map, not good. Basically, I spent 2 months full-time work on this. I started, I wasn't sure what I'm going to do with this, but I was like, okay, I need to continue. And I continued for 2 months. And then one day it was just, okay, it's not done, it's not useful, but I felt I have learned what I wanted to learn now at the time. I basically just closed Emacs and went on with my life. Okay, so quick recap for people who haven't coded x86 ASM in the modern days. So modern assembler has 16 64-bit registers. It has 16 so-called XMM, kind of multimedia, like SIMD registers. So in modern assembly, you usually do all your floating point in these registers. And you can do all other kind of funky single instruction, multiple data with them as well. There is the old, I don't know what I call it, 87, like x87, which is like the classic FPU, which is like if you had a 386 SX, you didn't have it. If you had a 386 DX, you got your FPU. It's not used very much anymore, apparently. I didn't know this. I thought, like, okay, I knew stuff, but no, this is totally different. And this, like, it's a complex instruction set computing. It's almost like 1,000 instructions in modern assembly. Like, there's not 1,000 mnemonics, but different ways they can be encoded, and you can actually, like, so it's a big, big language. Like, it's no, like, okay, so you have to find your subset and be comfortable with it, and basically, like, ignore that the rest of the stuff exists. But very often you're like, this seems interesting. There's probably an instruction for this, and you kind of just Google and Google and Google, and eventually, this is exactly the instruction I want. Here's an example of some instruction which actually used in the handwritten code myself. So you have like move, which is, I'm not sure how much assembly people know, but like move moves things between registers, jump, unconditional jump, add adds integers, XOR, bit test and set. These instructions are really cool. Like they basically like to test if a specific bit in your word or in your byte is set, and in that case kind of sets a flag, and you can do various jumps based on this. Load effective address, loads an address from shift left, jump less than equal. So basically, these other ones are kind of SIMD instructions. So mul SD means like multiply single double or scalar double, I think. So basically, these are the ones you use with XMM mirrors. There's all these other ones. Okay, the stack goes downwards. I will show you soon what that means. But basically means that you establish the stack pointer high in the memory somewhere, and when you call functions, the stack will grow here. And then basically when there's nothing to grow into, you get the stack overflow. There's like something called the ABI published by AMD, which basically created the 64-bit version of Intel, I guess, or not Intel, but of x86. So they tell you, like in assembly, you can do whatever you want. Like so, but there's still conventions. So if you want to stick to the conventions, you call your functions like this. You put things in these registers, and if you have more than 6 arguments, you push them down on the stack. And in that way, the function you call knows where to look for your arguments, basically. There are a lot of other calling conventions pertaining to the XMM stuff, but I don't use that, because in my world, everything is boxed, and we'll see that soon. You return your values, so basically whenever an expression by convention or an actual function returns, you put whatever you want to return in REX. And if you have multiple return values, which Scheme has, so it's lucky that they actually support this, they put the other value in RDX. So the way I do it in my scheme is that this is basically like car and coder. In REX, I put the first, normally the only return value. If there are more than ones, I put a list of the rest in RDX. Okay, so this stack register use is very important when you start coding assembly by hand. Like, and there's also the reason you don't want to code assembly by hand. It's not so much that it's hard to understand a single function, but it's like it's very quickly becomes unwieldy. Like you accidentally, so these registers I'm listing here, you need to store them if you want to use them, okay? So the caller has to, or rather the callee has to restore these registers. So the caller cannot see that someone has changed the register. So you can basically rely on that these registers are. So now here I have not that much time. I'm actually just only starting getting into my thing. So okay, I'm going to skip this very quickly. This is how the registers look. You have like a 64-bit registers and power. Here, how the scheme primitives have write by hand look. So they have a slightly different thing. And you can see here, like there's like macros in GNU assembler. So I decided there are 2 different main syntaxes, GNU and Intel. I went for GNU because I just wanted to have, if you write Intel syntax, which is quite more popular by people who write assembly by hand, you need to pick an assembler and need to install that assembler. I didn't want to do that, so this is GNU syntax. But anyway, you have macros. So they are basically just normal expansion, like string replacement macros. So basically, the second you feel like, oh, this code actually works, you extract into macros. It actually becomes relatively manageable. But the problem, of course, is that inside these macros, you cannot really see which register are used. You need to be very, very precise about which register you would use inside a macro or not. Okay, here's the example. So I realized, because I don't have enough time, so maybe I'm not going to stop here, but let's at least try to get this slide right. So basically, I let the assembler assemble these assembly instructions into data when I compile my program. I will then have these, so basically this push move sub here, that will be a string of bytes, which will sit at this label. And then during runtime, I basically just grab these bytes and puzzle together the functions I want to build. So let's just try to show you a quick example of this. So my idea is to walk you through this, which is like plus 2x, but maybe that's going to take a bit too long. So it's a very simple function, right? So you establish, this next slide I'm going to explain what it means. You need to establish, or rather save away, the caller's frame. So this RBP is basically the frame pointer by convention. You copy the stack pointer to the caller frame to basically establish your own frame. And then you need to allocate. So this basically, when you want to allocate local variables, like this is what a C compiler would do, you put them under your stack pointer. This looks like this. I'm trying to draw a diagram here. So basically, this line here, RSP, that's where the stack pointer currently is. RBP, that's the current, these dots here on the right, that's the current frame. The previous frame will look similar to this, but it's on top of that. The return address, which sits right at the top, the call instruction will push that onto the stack. So basically, when you do a ret, what that does, it pops the stack and jumps back to that address, right? There's something called a red zone, but that's, yeah, we don't need to go into that. So you can see here the X is accessed from RBP. So RBP sits statically while the function is executing, and you can access your local variables by offsetting from RBP. RSP will, which is a stack, will keep growing downwards, and if you call a new function, you establish a new frame and it grows downwards. And then when you pop, or basically return, it will pop up them again. Okay, so my basically idea was to show you how this function is actually, how I generate. So this generation here is not, I don't generate assembly, I generate using these puzzle pieces. I take the data, or take the bytes, and basically just string them together. So, but I've decompiled them for simplicity for the talk. So I check the arity, so I have this convention. I provide the arity of the method I call, or the function I call, in AL. So I check. We're calling this lambda, just to recap. We're calling this lambda, which has takes one argument. So I'm checking, is there one argument? If there is, jump to 24. Otherwise, this address here is the arity error exception handler. Call that. Otherwise, as shown, store this argument. RDI contains the first argument in offset 8 from RBP, below RBP. That's where X is going to live. Then this is totally unnecessary. So these kind of things I cannot really do. I cannot optimize easily. So it becomes very stupid because I just connect these different small pieces together. So you have directly move the X into the second position of the second argument for the call. This is a 2, the integer of 2, boxed, non-boxed. I'm going to explain what that means. Move that to RDI. So RDI takes the first argument, RSI takes the second argument. We're now going to call plus, right? So the second argument plus is the X we got passed. The first argument plus is the 2, which is a constant. This is the constant, so it's already compiled into the code. So here's how NaN boxing works. So the top line here is a NaN, it's not a number, which is basically a double. So the thing is, once you have a double which marks not a number, you can use the zeros and put stuff in them. This would still be a double, a valid, not a number, but you kind of so this is a kind of an established technique several dynamic languages use to basically tell the runtime what is the type of what I'm looking at. So this second line, it doesn't look, you cannot see that maybe, but it's an 8 there in the middle, or towards the left. That's the tag for 32-bit integer. And then it's just a 2, so I use the 32-bit integer as just the lower half of this value, this 64-bit value. So that plus, or rather ORed together, becomes this. So that's my tagged scheme value. This is an old school established Lisp technique how to kind of pass things around. Because this could be a pointer, this could be a list, this could be many different things, right? So, but at this point, because of this 8, which is the integer tag, I know that this 2 means that it's just a tagged value, it's just a normal integer. Okay, ignore that. Okay, so I have a symbol table, so whenever time you par, the reader creates new IDs. So ID 60 hex here is the plus. This is the reference of the symbol table. That happens to be the address of the symbol table. EX now contains 60. My stride is 8 because these are long words. These are 64-bit things. So what that will do, it will move whatever plus is at the moment into R10. Hopefully that is a function. This is null with the tag. This happens to be the list tag, but the list doesn't point anywhere, so I know that this is null. I compare, is the value of plus null? If not, jump further. Otherwise, the symbol is not defined, so call symbol not defined here. This again is the symbol not defined handler. This again, all of this generated at runtime, right? So I generate all this based on the snippets at runtime, and then I call into this function to actually run it. This is just decompiled for readability. Okay, plus is defined. So move it into Rx. Again, Rx is kind of like the conventional place for the expression return value. I remove the tag by shifting. So basically, the tag is in the upper bits. So just shift everything 10 or 16 bits to the left, shift it back, gone. Okay, convention, like if you take one thing from this talk, convention to clear a register, you XOR it with itself. Then, as I mentioned, in AEL, I put a number of arguments. There are 2 arguments to plus. So basically, this is before calling it. I restore the stack, and the reason I'm doing this usually happens afterwards, but because my compiler is smart enough to figure out that this is a tail call, so we don't need a stack. No one's going to return to us. So you get rid of the stack, and then just jump instead of call. Just jump into the same function. That will mean that when the function I'm calling, in this case plus, when it returns, it will return to the function that called me, right? I removed the existence of myself from the stack. So this is one way to implement tail call implementation. It's much simpler, because I started with a much more complicated way, which was based on like knowledge from Java and exceptions and complication. It's like, no, in assembly you can just do this. Okay, cool. And here's like dead code, which, because normally if there's been a call, you would have reached there, cleared out the stack, and then returned. But you have already done that. So this is gone. Okay, here's like a recap. Here's like all the generated code for plus 2x, lambda plus 2x, which I just walked through. Okay, quick reflection. My impression after doing all this is like while trying to reach for simplicity and trying to go down to the hardware, if a modern CPU is so complex, you're basically just calling to quite advanced API and lots of conventions. You cannot really get very close to it. It's like it's an entire career and knowledge to actually get close to this thing. So for me, it felt like, okay, I'm just coding to a very high-level API, which hides the actual 40 years of x86 evolution behind it. As I mentioned, you need to be very, so like this is something that comes back from my closure, like based on my experience of programming. You need to be very strict in assembly. Like if you don't know what was going on, it will crash directly, right? Like so, you have to establish conventions for, like, I always know that this value is going to be in this register, like basically this is going to be in RBX, the first argument is going to be in this register, all these things. So otherwise you cannot scale it up. Like it took me a long time to establish this. Maybe the first months I just tried to get anything working. I couldn't establish. Then once you establish this layer, I could eventually build a little scheme compiler on top of it, but it was quite hard. So yeah, testing is fundamental, as you can imagine. Like anything can go wrong at any time. It's very hard to get, like, very easy to get drift, like you realize, oh, everything seems to be working, and then you realize, oh, but if you call this function, everything crashes. Yeah, as mentioned before, it's very tempting to introduce more complexity to make the compiler more advanced, but that itself, like, because assembly is quite gritty, it's very hard for you to build in, like, abstractions in it. You need to keep it simple, so otherwise you lose control of what you're doing. So maybe, I think, like, after these 2 months, if I take a break for a year, maybe if I revisit it, I could be able to do that. Yeah, again, you can easily introduce a change. You're trying to do some smaller factoring and realize, like, oh, no, like, I've started drifting away. Like, there's no way to know what's going wrong. Like, everything just crashes. This could be a simple typing mistake. It could be a logical error. Like, you have no way to know. You could try to debug it, but that's quite time-consuming. So basically, I always start from a very firm base, throw it away. And I'm not sure if I would have done this when I was younger. Like, I think I would just sit around code all night and still not get anywhere. Yes, again, soon I have this kind of, this is not so much about assembly, but I have this kind of habit of, like, just the final change before my commit. Like, as if the commit was costly, right? Like, it's like, just put in something more. Okay, no, actually, I like it this better, and then you kind of lose an entire session of programming almost. Like, so this is not something you want to do when you code assembler. Yeah, so my conclusion is simple, false. This is not like trying to throw, it's very tempting to go get rid of all the abstraction, go down layers, but my impression is almost like that train has sailed, so to speak. So it has left the station or the harbor. So it's like, we kind of, I'm not sure what to do anymore about this. But I felt that this was necessary for me at this point in my career and my life to revisit, get a firm understanding of my foundations, firm for me, right? Like, it's still kind of like me tinkering around, writing a small assembly program. But it's like, I felt it was really useful to revisit this for me. And I think that now I kind of have more appreciation, taking a step back, ready to, I actually went back to work on another normal closure project after this and felt very, oh my God, it's like you can write a function which actually does something without crashing. Okay, so if you're interested in more of this, you can look here. Okay, thank you very much.